All right, let's just dive right into this explainer. We spend so much time talking about how machines generate text or make pretty pictures, but today we're looking at something way more profound. We're talking about a literal shift in how machines actually think. We're exploring the absolute bleeding edge of causal AI, which is this wild field where researchers are building systems that actually understand cause and effect rather than just, memorizing patterns.
Because look, while the whole tech world is obsessing over the newest chatbots, the real question, the one we actually need to be asking, is what comes next? And the answer comes down to a massive limitation with AI today. We have to teach a machine not just what is happening in a data set, but why it's happening. Current models are amazing at telling you two things happen at the same time, but they totally stumble when you ask them what caused what. Causality is for sure the next frontier.
And that actually brings us to a seriously monumental event that just wrapped up at the Broad Institute of MIT and Harvard, the 2026 CLEAR Conference. The Conference on Causal Learning and Reasoning is basically where the brightest minds on the planet get together to solve this exact problem. The proceedings from this 5th annual conference just dropped, and let me tell you, they are absolutely packed with breakthroughs on how we engineer actual reasoning into machine learning.
So we are going to distill over 30 of these incredibly dense academic papers into 4 main themes: advancing core causal theory, AI and healthcare applications, generative AI and LLMs, and finally, the future of causal reasoning. Let's get into it.
Section 1, Advancing Core Causal Theory.
Okay, so there's a term you'd hear constantly if you were at this conference, and it's DAG, Directed Acyclic Graph. Think of a DAG like a giant family tree, but for data. It's this mathematical blueprint where arrows point directly from a cause to an effect. The acyclic part just means no loops allowed. An effect can't travel back in time to cause itself, right? But the really huge challenge right now is something called causal discovery. Basically, how do we build algorithms that act like detectives? Tools that can sift through massive, messy datasets and automatically draw these causal maps totally from scratch.
And scientists are completely rethinking how these discovery tools actually search for those maps. Take differentiable causal search, for example. In the past, finding a DEG meant brutally testing every single possible combination of variables one by one. Super slow, super clunky. But by making the search differentiable, researchers are turning it into this smooth mathematical landscape. The algorithm can basically just glide rapidly down the steepest slopes of the data to pinpoint the exact causal structure even in insanely complex systems.
The crucial point here is that they aren't just tweaking old algorithms, they are inventing entirely new mathematics. Instead of just assuming relationships are simple straight lines, they're using these advanced kernel measures. Basically, think of them as mathematical filters that let the AI detect hidden, curved, and incredibly complex relationships. These causal discovery tools are getting sharper, faster, and just vastly more capable of mapping out the invisible forces connecting our world.
All right, moving on to Section 2. AI in healthcare applications.
So, let's take those discovery tools out of the lab and into the real world. We're seeing a really clear pipeline emerge here. First, data fusion brings together highly complex electronic health records. Then, and this is mind-blowing, we get causal feature generation. Researchers are actively generating counterfactual chest x-rays. That means an AI can literally show a doctor, hey, here is exactly what this patient's lungs would look like if we had intervened differently, which naturally leads straight into super robust, evidence-based clinical decision-making.
To put this in perspective, one standout paper presented a causal framework specifically for pharmacovigilance. Their discovery tool is purpose-built to hunt down severe drug side effects, like drug-induced acute kidney injury, that are just hiding inside massive medical databases. A normal AI might flag a drug just because, well, sick people tend to take it. But causal AI tools actually disentangle the underlying sickness from the drug itself to pinpoint the true cause of the injury. It's a real game changer.
I absolutely love this paper title because it hits the nail on the head as to why this matters. In medicine, we are constantly fighting multimodal confounding. Actually, scratch the jargon. That's just a fancy way of saying there are a million hidden variables, from genetics to what you ate for breakfast, messing up the data. We have to know the true treatment effect. Did the pill actually cure the patient, or was it something else entirely? Causal discovery tools are what make that valid inference possible. Which leads us right into Section 3, Generative AI and LLMs.
We are witnessing a massive shift in how these models are built. Traditional generative AI relies on statistical information interpolation. That basically means the AI is just guessing the next word based on massive scale and pattern matching. It's an illusion of reasoning. But this new research introduces causal articulation theory. This literally forces the AI to articulate static and temporal causal models before it even speaks. We're moving from a parrot, mimicking words, to an engine that actually understands the underlying physics of a sentence.
Get this. One paper detailed a fascinating concept, using the AI as an actual co-scientist. They built a multi-agent LLM framework specifically for causal discovery. So instead of a human manually coding a search algorithm, multiple AI agents are prompted to debate and reason with each other. They actively formulate hypotheses and run mathematical tests to discover hidden causal variables in scientific experiments. The LLM isn't just the chat interface anymore. It is the discovery tool itself.
All these CLER 2026 proceedings prove that researchers are successfully forcing generative AI to drop the simple, post hoc rationalizations. By implementing simulation-based inference and unveiling causal calibration across different sizes of LLMs, we're stepping into an era of true structural discovery. The AI isn't just spitting out text that sounds plausible. It's generating text based on a mathematically verified map of cause and effect.
And finally, let's look at Section 4, the future of causal reasoning. Because causality is aggressively expanding way beyond just text and medicine into the hard sciences. We're talking physics-informed machine learning, where causal tools ensure the AI actually respects the laws of thermodynamics. They're using spatial partitioning to map out wildly complex climate systems. We're seeing robust bandit policies improving how robots learn. And, this is huge, they're using causal tools for counterfactual fairness. That means we can mathematically prove if an AI's decision would have changed if a person's race or gender were different, which directly tackles algorithmic bias.
Our ultimate goal is captured so perfectly in this paper's title: creating AI models that are actually faithful to their domain. See, when an AI only knows patterns, it breaks the second the real world changes. But through counterfactually robust learning, an AI understands the underlying reality of its domain. It knows what happens if you tweak a variable, making it vastly more reliable and safe in unpredictable, messy, real-world scenarios.
34. That is the number of pioneering, highly technical papers accepted at this single event in Cambridge. 34 massive leaps forward in a very short amount of time. It's a loud and clear signal that the causal revolution isn't just some distant theoretical dream anymore. It is a highly specialized, rapidly maturing field that is moving at an absolute breakneck pace. So, as you process all these incredible insights from Clear 2026, I want to leave you with this one thought. For decades, we've been totally satisfied with machines that observe the world and tell us what is. But as we cross the threshold into systems that can actually ask why did it happen, the whole paradigm shifts. When machines finally understand cause and effect, what human problem will they solve next?